Hi, so I'm a third year PhD student here at the CBU, and today I want to talk to you about DCM with MRS. Now, to start off, if you've never come across DCM before, you don't know what it stands for, don't worry, we're going to start there. Does not stand for, as someone once asked me at a conference, dastardly complex methods. However, it is a complaint that I see levelled at DCM quite a bit. A lot of people accuse DCM of being a bit of a black box, and that technically isn't true. You can look at all the equations behind it, but unless you have some form of an advanced mathematics degree, I will absolutely guarantee it's difficult to do. So today what I want to do is shine a bit of a light into the black box of DCM and hopefully make it just a slightly lighter shade of grey by the time you leave here today. So to start off, what does DCM actually stand for? DCM stands for Dynamic Causal Modelling. And it's dynamic in that we're looking at how neural activity changes over time. It's causal in that we're interested in the effective connectivity in the brain, how activity in one region can affect activity in subsequent regions, and how that can be changed by external perturbations. And it's modelling in that we use mathematical equations to try and understand the mechanisms that might underpin activity we see at a sensor level in our imaging data. So today I'm going to have a look at all the components that make up DCM, and then right at the end, briefly go into how we can combine that with other neuroimaging data other than MEG in order to make our models hit that little bit better. So, step one, the model itself. Now, I could use a brain analogy to talk to you about brain modelling, but where's life without a bit of whimsy? So I'll instead be using this. Let's say, come on with me on a journey here. Imagine you're out on a boat in the middle of nowhere with a brand new seismographer or something like that can send signals down to the ocean floor and receive signals back to try and tell you a little bit of information about what might be down there. And whilst going through a relatively uncharted bit of territory, you get a strange signal coming up from the bottom of the ocean. And you realise that strange signal could absolutely be caused by just regular flora and fauna, but it could also be caused by the lost city of Atlantis. And what you really want to know is whether that signal that you've received is caused by regular ocean goings-on or something potentially groundbreaking. And ideally, you don't only want to know which model is more likely, you also want the level of certainty you can have that you're right before you start running to the nearest university claiming to have found a lost civilization, or send down divers, which we know from the forgotten classic Atlantis can be incredibly dangerous. So, how do we tell the difference between these two things? It's an ill-posed problem, you don't have a lot of information. So the first thing you decide to do is send out a few more boats. And you come to the decision that the easiest way to determine what's down there is going to be to look at the interaction between these three regions in the ocean. And here sources differ, but they seem to agree that the lost city of Atlantis is in some way cut off from the rest of the ocean. Could be a force field, some massive glass dish, we're unsure, but it's in some way disconnected from the rest of the ocean. So if a current comes in, it will be stopped by the city, and you won't see the regions interconnected in the same way as you would if there's normal ocean flora and fauna, in which case all the three regions from your boats will be connected by each other. So from this you get two different hypotheses. Hypothesis one, the boring one, there is no lost city of Atlantis, and the three regions of interest of our three boats are interconnected with each other. Or, the far more interesting hypothesis two, Atlantis exists, and the three regions of interest are not interconnected because Atlantis is stopping those ocean currents. Now, in order to turn this into something that we can model, we first need to introduce a bit of maths. So, this is the first equation we'll come across. This is basically characterising what exactly might be going on the ocean floor. Here, z dot t is the rate of change in our activity depending on what's happening in the world. So, we have our rate of activity changing as modelled by over time of our three boats, as modelled by a combination of JT, which is a connectivity matrix describing how our three regions are connected, and an external input, in this case our ocean current. So essentially what this equation is doing is characterising how our ocean floor is behaving given an external input and how that external input propagates through the system. But JT is where we can get a lot of our really good information. So JT is our connectivity matrix, which means it's categorizing how these three regions of interest are connected together. In the case of our regular flora and fauna, we might say that region 1 and region 2 are connected, represented by 1s in this matrix. whereas that isn't the case for Atlantis. Nothing is connected, so we see zeros. And this is where we can really start to model those hypotheses that we came to earlier. And if we switch out ocean themes for a brain, we can start to see how this might be useful. We're able to characterize how different regions of the brain might be connected or not connected using dynamic causal modeling. And going beyond this macro scale look at brain networks, we can also zoom in to investigate the contribution of individual neuronal populations to the signal that we see. There are lots of different options with DCM models of which one you pick. They'll have different types of neuronal populations, different numbers of neural populations. A lot of them will have 4, like this one here, based on the information we know from the structure of the cortical column. But some might have 3, and others go a little bit further and also allow you to investigate the potential contribution of neurotransmitters, such as GABA and glutamate, to that sensor level data. So that's our model. We can characterize it quite simply with this equation. There's a lot more maths under the surface. And we can have our macroscale model of brain networks, which is constructed with mesoscale models of neuronal dynamics. So now we have our model, we need to introduce it to some data. Now, the data, first of all, needs its own equation, because we need to characterize how we go from data that is actually in the brain, or in this case, the ocean floor, to what we get at our sensors. So here, Y is our sensor level data that we receive up on our boats. Z is the activity down at the ocean floor, and we want to know how we map one onto the other, and we do that with theta. That will vary depending on what kind of data you're using. In our silly analogy here, it might be how many fish get in the way, or how much data is lost as it travels through water. Whereas for our things like fMRI, we use the hemodynamic response. For MEG, we can model a few data features with DCM. The first one, classically ERPs. As we've seen, if you've got a well-characterized task, something like the mismatch negativity, which has a well-characterized response, then you can use ERPs and put those as your data feature of interest into a DCM. But if you're looking at a new task, which maybe isn't quite as well-characterized, or at resting state data, we can also look at frequency information using power spectra to investigate how different frequencies might propagate throughout the brain. And with these two models, the model of what our system is doing and how we get from our data down in that system to the data we get at our sensors, we're then able to do two things. The first thing is that we can identify our model parameters. In this case, that might be the strength of connections between neuronal populations or between brain regions. And we can calculate our model evidence. Now, our model evidence is a key part of DCM. Essentially, what model evidence is doing is saying, all right, I don't really care how good each individual parameter is at modeling our data. That's not what I'm interested in. What I want to know is how good is the model as a whole, irrespective of all those parameters, how good is the model? Because that allows you to compare models which have different numbers of parameters or entirely different parameters on a level playing field. So what we would do is we calculate our model evidence, and that allows us to determine which model, Atlantis or not, is the best model of our data that we get. So ideally, when we're talking about how to make models better, when we're talking about DCM, what we want to say is we want improved model evidence. However, you reach a little bit of a snag here. Because to get model evidence, what you need to do mathematically is this. And this is saying exactly what I just said. It's saying that irrespective of the parameters, I don't care what the parameters are, I want to look across them all to look at how good my model is. But to do that is a little teensy bit mathematically impossible. So RIP DCM, that's it, our hopes and dreams are dead. We can't actually calculate model evidence to realize how good our models are. So what we instead do is we approximate our model evidence with free energy. The intuition behind free energy is that it is the difference between our prediction based on our model and what we actually get from our data. So by minimizing our free energy, the difference between these two things, we will always maximize our model evidence. The better our model is, the better predictions it makes, the lower free energy becomes. However, free energy isn't only interested in how accurate your model is. It's also interested in how complicated it is. If we go back to our ERP that we had later and sample some random little data points from it, and then get rid of it because we don't know what that's actually there, and we try and model it, we can start off with something really simple like a straight line. And we get, well, it's not particularly accurate, it's missing quite a lot of the points, but it's also very low complexity, so it's doing a decent job. If we make something a little bit more complex, we can hit even more of our points, more accurate but also more complex. And we can keep going until we end up with something that's really complicated but also very accurate. If we looked at accuracy only, this would be our best model so far. It's hitting all of our data points, but it's also ridiculously complicated. So free energy helps us look for not just the optimal model, the best model, but the most parsimonious model. It's that trade-off between accuracy and complexity that free energy does really well. So we can't look at model evidence technically, so we approximate it with free energy. And now we have all the components in order to fit our model. We have our model, the data, and the benchmark with which to fit it to. And now we can begin fitting our model like we do with most models. We vary parameters in order to improve our free energy and iteratively continue doing that until we reach something that we're happy with, that reaches a threshold where we say that this is a good model of our data. And this is super easy when it's a graphic on a slide, but obviously in real life, there's a bit more complexity involved. We make a lot of assumptions and shortcuts in order to be able to make this modeling computationally tractable. For example, we assume that a lot of our parameters, our noise parameters, for example, are normally distributed. And we acknowledge that globally, the brain probably isn't normally distributed, but we assume that locally, it's probably good enough to say that things are Gaussian. In the same way that we know that the world is a sphere at large, but it's usually good enough when you're building something to say that it's flat. If you're curious about the kind of assumptions and shortcuts that we make in order to fit our models, I recommend this paper on variational Laplace, which does a reasonably good job of going through it without assuming any prior knowledge of mathematics. So that's DCM. What about the MRS? Well, so far, all we've done is kind of for one person. So what we want to do now is incorporate data beyond our MEG signal in order to improve our model further. We know that there is much more information that we can get about the brain than from a single MEG signal. So how do we incorporate that in to improve our models? And because we use Bayes, of course, we do it by incorporating into our prior approximations, our prior expectations. So at a single level DCM, that kind of first level, a lot of our prior expectations are based on neurophysiological data that we know of, things like firing rate of neurons. But if we go to our second level, we can start to incorporate population level statistics, such as, for example, a diagnostic group, or whether we have baseline versus follow-up, or on and off drug, or even neurotransmitter levels as measured by spectroscopy. And the hope here is that by incorporating these things, we not only make our models better because we're giving it more information, but we can also identify the area of our model where these individual differences are felt. Whereabouts in our neural dynamics are these individual differences a thing? So why MRS? Well, for our purposes, we know that certain neurochemicals are depleted in the brains of our patients, including GABA, which we can measure directly using 7T spectroscopy, and noradrenaline, which we can't directly measure, so we get a proxy of it by measuring the integrity of the locus ceruleus, which is a brain area that produces noradrenaline. And our hope is that by including this information into our model of brain function, we can identify where exactly in the brain we're seeing these effects. So ideally, you'd expect to see it on GABA, but what kind of downstream effects might that have on connectivity, both within those neuronal populations and at the brain at large? So in my study, we ask patients and controls to do a task in the MEG scanner of apathy. We then model this using our second level DCM of using parametric empirical Bayes to identify which is the best model of the brain when they're doing this task. And we can then incorporate additional information from spectroscopy, such as GABA density and locus ceruleus integrity, to improve our models and ask where these individual differences are felt. And we also incorporate behavioral analyses to investigate whether the mechanisms that we've identified might also be the same way that the brain solves the problem, with the expectation that if we've hit on something, we'd expect that including this behavioral level analysis will further improve the quality of our model. With that, I'd like to thank Cool, that worked out well. With that, I'd like to thank everyone in the lab and everyone who's helped me get to grips with DCM, in particular Amir, Pranay and James, and I'll happily take any questions that you have.